Let's take a look at some more applications of exponential and logarithmic functions. So we're going to look at cobalt here. It has several isotopes, and one of these, cobalt 60, is radioactive and has a half-life of 5.7 years. All right. Used to trace the path of non-radioactive substances in a system. So very useful for in some scientific areas. We are going to write the equation of decay, and we're going to find the percentage left after 8 years. And then we want to find out how many years to fall to 5% of the original amount. Well, let's start off with the equation of the function based on time, or rather the amount that we're reaching that will be at a certain time, is a e to the kt. Now, k could be a negative, and sometimes it's put in with a negative, but I won't do that because when we solve for it, we will get a negative number for k, and that will suffice because that will go in that place for k. So we know certain things. So from up here, whatever the original amount is, half of that, half of that amount will be at 5.7 years. Okay, so think of it as time and then the function of the time or the result, the y value. So the time here is 5.7 and 1/2 a. And we are going to use that. Yeah. And so we're going to say that the function at 5.7 5.7 years is the original amount, which we don't know, times e, and then 5.7 times k. But that original amount is 1/2 of the amount, or no, rather 5.7 years, you have 1/2 of the original amount. So we have put this in it, and we have put this in it. By doing so, we now can divide both sides by a, and we are left with 1/2 equals e to the 5.7k. So what we now can do is figure out what the k is, because it's the only variable left. Let's take the natural log of 1/2, or 0.5, your preference, and the natural log of e to the 5.7k, because that allows, with the natural log of e, that allows that is equal to 5.7k. So now we will say 5.7k, natural log of 0.5, or 1/2, choice. And now we'll divide by 5.7. And we get that k is approximately negative 0.1216, 4 decimal places, of course. So we get an equation, the answer to letter A above, is that the function of time is equal to the original amount, e, negative 0.1216t. And then we will use that equation for B. So I am going to draw a line down through here, and we'll have some space for B to work with. So this was letter A that we worked out. Now let's do letter B. And we need the equation. The function of time is equal to A, E, negative 0.1216. I have that right. T. And what we want to know after 8 years. So we're going to say T is equal to 8. Um, So we're going to keep the same. We don't know the percentage, so actually let's talk about that. That's what I'm thinking of here, is we know that A is the original amount. We want to know what percent. So we're going to do XA so that X is equal to a percent amount, such as, say it was 17%. So 17 would be equal to X, or actually 0.17. And so we'd have 0.17A. So we're trying to find out, it'd be like 0.17A would be 17% of the original amount. Well, we don't know what that original amount is, but we do know we're trying to get the percent. So our goal is to figure out what X is here. And so this is the reason I did X times A as if it was a 0.17, like 17%. But we don't know what percent yet, but we'll solve for it. Because now we can do AE negative 0.1216 and the 8th power. So we have as the variables A's and X, but divide both sides by A, and we don't have that anymore. So now we have X is equal to E negative 0.1216 times 8. So now we can put this into the calculator and it'll tell us what X is. And X comes to approximately 0.37802. Whoops, I put one meant to put 0. And we go 4 decimal places, and the 2 does not round the 0 up. So we have 0.3780. And to make that a percent, we'll move the decimal twice. So we have 37.8%. And that will be after 8 years. After 8 years. You could even write that as 8 years. And, well, no, that's supposed to be the amount, so ignore that. And let's now look at C. So for C, how many years does it take for the amount to fall to 5%? Well, 5%, it's 5% of A, which is 0.05 of A. So we want that that's going to be the amount that we're trying to get to. And the formula is AE to the negative 0.1216 T. So the A's cancel out. And now what we have is just one single variable. So we need to solve for that. That means if we have 0.05 equals E to the negative 0.1216 T, we are applying natural log to both so that with this part comes down to the main part of the equation. And so we have natural log of 0.05 equals negative 0.1216T, divide by negative 0.1216, negative 0.1216. Okay. And that cancels out. So now we have T is approximately, when we do natural log of 0.05 divided by negative 0.1216, we get 24.6559 and so on, actually 62. So that's 24 and about a half years. So it's closer to 25 than 24, except that it's more like a half year. So we could say about 25 years. Or we could say about 24 and a half years, and we'd be a little bit more precise with that. That would be a better answer, or appropriate. So this is a half-life and 5% type of problem. Let's take a look at a different type of thing now. So we are looking at bacteria growing. There's 1,000 initial cells, because that's the initial amount or initial time at 0 at the beginning. That's 1,000. And then we also have, after 40 minutes, 1,650 cells. So let's write the equation. How much in 2 hours? How much time to get to 10,000? So for A, the function of time, the result rather, if we use the time, is equal to A, E, K, T. So we know that the A is 1,000. Okay, so then we also know this. So we can get the K by plugging in all of that. First, I'll rewrite this as 1,000 E K T, and now we'll put in 40 and 1,650. So 1,650 is the result when the time is 40 minutes. Right, so divide by the 1,000. Okay, so we get 1.65 is equal to E to the 40t. This is where we'll apply the natural log. And we get 40t and divide by the 40. So, oh, I've been writing 40. Hold on. The t is 40, but that means this is k. K, because it's the k that we're trying to get right now. And one natural log of 1.65 divided by 40 means the k is approximately 0.0125. This k is positive now because this is an increase. So what we have for equation is that the function of time is 1,000 E 0.125. Oh, there's an extra zero in here. Be careful with those extra zeros that you miss them. But here is our equation. And now let's use it for the other two things. So for B, in 2 hours. So the equation Ft equals 1,000 E to the 0.0125t. So the function after 2 hours. Now, let's think about this for a moment. E 0.0125. And for the time, well, this is hours. But when we set up the problem, we did it with minutes. So we actually have to change that. So it's a function of 120 because there's 60 minutes an hour. And that means that there are 120 minutes for the 2 hours. So that's what we need in this case there. But having done that now, we can solve for it. The function in 120 is all of this in the calculator. So you do e to exponent all that power and then multiply by 1,000. That comes to 400, approximately 4,481. So that means that in 2 hours, 4,481 bacteria. Okay, now the last part. It's going to be 10,000, so that will be the result, and that's going to be equal to the original 1,000, E 0.0125t. So we want to find out how much time it will take to get to that. So here is like the coordinate point version of it. So we need to find the t. And we can do that now. We have to get the t out of there. Let's first divide by 1,000, which we get 10. 0.12, whoops, I forgot the zero again. Gotta be careful of that every time. 0.125t. And we do natural log of both sides because that allows this part to come down to the main part of the problem. Natural log of 10, 0.0125t. 0.125t crosses out. 0.0125. And then you put that in the calculator and you get t is approximately 184. But remember that that's minutes. Well, we don't talk in terms of 184 minutes. We don't say, oh, it takes 184 minutes to do this. Instead, 60 minutes an hour, that's 3 hours and 4 minutes to get 10,000 bacteria. Okay, so a biologist is loving this because they want to see the growth of the bacteria. But in our case, we just found the numbers right. And we now know it. Okay, let's take a look at the last problem here, which is a population growth, in this case of animals. It's going to be the same type of thing. So there's one pair of rabbits, that means there's two of them, at the beginning. So at the beginning, there are 2 rabbits. After 8 years, there's 160. So let's do the equation. How much in 10 years and how many years to get 5,000? So the equation, the function of time, equals AE KT. So the A we know is 2, that's the beginning. So the function of time is 2E KT. And now we will use the 8 and the 160. So 160 will be the result when it's 8 years. And divide by 2, and we have an 80. And do natural log. So we have the natural log of 80 equals 8k, and we'll divide by 8 so that we can find out what the k is. So when you put this in the calculator, you get the k is approximately 0.5478. So the equation is that the function for time is equal to 2e 0.5478 t. And all we have to know is the amount of time, and we can find out excuse me, how many rabbits that there will be. So let's come up here and let's do B. That was A. And let's write out that equation again. 0.5478t. I believe that's what I have. And we know for this one, t is 10 years. So the function of time is 2e 0.5478 times 10. And you put that into the calculator, and you get the result of about 478 rabbits. Okay. And so it goes pretty fast in 2 years, from 60 to 478. So it's one of these, like, start with 2, and it's a little slower growth, and then as it gets higher, it goes up faster. Whoops. Much faster. Now, C. How long will it take to get to 5,000? Well, that's going to be the result of it. So we're going to have the function of t is equal to 2e 0.5478 t. And in this case, what we know is that we want, what was it, 5,000? So we put 5,000 as a result, 0.5478 t, divide by 2, 5478 t, apply a natural log so that we can get the t to the main part of the equation. equals 0.5478t. Let's divide by that, 5.5478. So here it goes away, 0.5478. So we just have t left here. So t is approximately, when you work this out, is 14.28. So we would say 5,000 rabbits in a little more than 14 years. So you notice in almost all of these problems, one key part of it is using natural log to get the to get the variable down out of the exponent. Okay, and we end up doing that twice in these problems. You don't have to do it in this one over here, but you do have to do it again over here in order to get that t down. So most of the problems have that based upon whether where your variable knows. And that's the main key idea for solving the exponential and logarithmic functions, or especially these like practical application type things. Well, I hope that this has helped you with these. Thank you for watching and listening.